just gaze up at the night sky and wonder, how does light actually work? It's everywhere, yet it feels like one of the most, well, enigmatic things in the universe. Okay, let's unpack this. Our deep dive today is all about light and how it interacts with, well, everything around us, from the tiniest subatomic particles right up to the largest structures in the cosmos. And at its very core, light presents this mind-bending paradox. It's both a wave and a particle, depending on the circumstances. This idea, wave-particle duality, it's a real cornerstone of modern physics. So our mission today is to understand how this dual nature, how it reveals itself across these vastly different scales, and hopefully paint a unified yet wonderfully complex picture of reality.
Yeah, and what's fascinating here is that for centuries, scientists really battled over this. Was light made of particles or was it waves? It was a huge intellectual struggle. Back in the 17th century, Isaac Newton, for instance, he championed the idea of light as tiny particles, corpuscles, he called them. And his model was actually pretty good at explaining reflection, like a billiard ball bouncing off a cushion. He even tried to adapt it for refraction, how light bends going through glass or water, although, well, he had to incorrectly assume light sped up in denser stuff for his theory to work, which turned out to be wrong.
Right, that's the classic particle view. But then you had this other idea gaining ground, light as a wave, championed by Christiaan Huygens around the same time. And the really pivotal moment, the experiment that seemed to settle it for a while, came later, early 19th century, with Thomas Young's double-slit experiment. That's the famous one, right? When light went through two tiny slits, it didn't just make two bright spots. It created these interference patterns, bright and dark bands. Now that is classic wave behavior, like ripples crossing in a pond. A simple particle model just couldn't make sense of that at all. So what happened then?
Exactly. And the wave theory just kept explaining more things like diffraction, light bending around corners, and polarization too. The debate really seemed settled, definitively settled in the 1860s. James Clerk Maxwell came along with his equations for electromagnetism. Just beautiful equations. They didn't just predict electromagnetic waves moving at light speed. They identified light itself as one of these waves. So for the rest of the 19th century, pretty much everyone thought, okay, light is a wave, done.
Okay, but here's where it gets really interesting. Just when everyone thought, right, we've got light figured out, the 20th century just completely flipped the script. Quantum mechanics arose. New experiments started popping up. Things that the classical wave theory just couldn't explain. You had Max Planck back in 1900 trying to solve this thing called the ultraviolet catastrophe. Classical physics predicted hot things should glow infinitely bright in UV light, which obviously they don't. Planck's radical idea was that light energy could only come in discrete packets, or quanta. And then just 5 years later, Albert Einstein took that idea and ran with it. He used it to explain the photoelectric effect, basically proposing that light itself is made of these energy packets. We call them photons now. So how did that change everything? It sounds like we're back to particles again.
Well, yes and no. That's the crux of it. What's truly remarkable is that these findings brought back a particle-like nature to light, but not as a replacement for the wave theory. It was a complement. The modern understanding isn't about choosing, is light a wave or a particle? It's much more subtle. It's more like asking, under what conditions does light behave like a wave or like a particle? The genius insight, really, is that the experiment you set up determines which aspect of light you observe. Nature kind of provides an answer that fits the question you're asking it.
Okay, that sets the stage perfectly.
Yeah.
We've got this incredible dual nature. Now let's start our journey at the smallest scales imaginable. So what happens when light hits the quantum realm?
Right. Down at the microscopic level, when light interacts with, say, individual atoms or electrons, it really is best understood as these discrete, indivisible packets of energy photons. Interactions aren't smooth or continuous, they're distinct events. All or nothing kinds of things involving very specific amounts of energy and momentum being transferred. It's almost like light is delivering these tiny, precise kicks.
And the absolute classic example of this, the real poster child, is the photoelectric effect, right? Where light shining on a metal can knock electrons out. Classically, this thing was a complete puzzle, a real conundrum for scientists back then. Because, look, electrons were ejected instantly, even if the light was really dim. Classical wave theory predicted there should be a lag time, a weak wave would need time to build up enough energy to free an electron. But nope, it was instantaneous. And even weirder, the energy of those electrons flying off. Their maximum kinetic energy depended only on the light's frequency, its color, not how bright the light was. So if you turn up the intensity, you'd get more electrons, sure, but each one wouldn't be any more energetic. That just flew in the face of the wave idea, which said a more intense wave should deliver more energy. And then there was this other weird thing, this cutoff frequency. For any given metal, light below a certain frequency just wouldn't eject any electrons, no matter how bright you made it. So like a faint violet light might work, but a super intense red light wouldn't do a thing for some metals. It seemed totally backwards. So how did Einstein manage to crack this? It sounds impossible from a classical view.
Well, Einstein's quantum solution, the thing that actually won him his Nobel Prize, it just beautifully explained all these paradoxes in one go. He took Planck's idea seriously. The energy of a single photon is directly proportional to the light's frequency. E equals hf. So a violet photon, just plain, has more energy than a red photon. Simple as that. And the interaction is strictly one-to-one. A single photon gets absorbed by a single electron, transferring all its energy, all or nothing. That photon's energy then does two things. First, it has to overcome the work function. That's the energy needed just to pull the electron out of the metal. Think of it like an exit fee. Right. And whatever energy is left over becomes the electron's kinetic energy, how fast it moves. This simple picture immediately explained why you need a minimum frequency. The photon needs enough energy to pay the exit fee. And it explained why the electron's energy depends only on frequency, not intensity. More intensity just means more photons hitting per second, so more electrons get ejected. But each electron still only interacts with one photon.
Right, that makes sense. And to make it really concrete, different metals hold on to their electrons differently. They have different work functions. Your sources mentioned specific examples like sodium, silver, aluminum, cesium. So visible light, say between 400 and 700 nanometers, that can knock electrons out of cesium or sodium pretty easily. Their work functions are low enough. But even energetic violet light, down at 400 nanometers, it cannot get an electron out of silver. Why? Because silver just holds onto its electrons much more tightly. You need an even higher energy photon, like from UV light, to do the job.
Yeah.
It really shows this precise sort of dialogue between the light-specific energy packet and the material-specific properties. It's incredibly precise.
Absolutely. And this isn't just, some abstract physics concept. The photoelectric effect is fundamental to so much modern tech. Think about photomultiplier tubes, PMTs. They're super sensitive light detectors used in astronomy, medical imaging, all sorts of things. They work because one initial photoelectron gets accelerated and knocks out more electrons, creating a cascade, amplifying even a tiny light signal. Digital cameras, the sensors in them, same principle. Solar cells converting sunlight to electricity. Yep, photoelectric effect again. It's everywhere. It really is kind of mind-bending that so much of our tech relies on these tiny, fundamentally quantum interactions.
Okay, so photoelectric effect. Photons have discrete energy. Check. But then came Compton scattering, which proved they also carry discrete momentum, really cementing that particle picture. This was Arthur Compton in 1923. He saw something classical waves just couldn't do. When he shot high-energy photons like X-rays at electrons, the photons that bounced off, the scattered ones, had a longer wavelength, lower energy. And how much the wavelength changed depended on the angle they scattered at. Waves just shouldn't lose energy and change wavelength like that from a simple bounce.
Exactly. Compton's brilliant insight was to treat it not like a wave scattering, but like a collision. A perfectly elastic collision between two particles, a photon and an electron. He applied conservation of energy and conservation of momentum, just like you would for billiard balls colliding. And the key was assigning momentum to the photon itself. And crucially, he linked that particle-like momentum to its wavelength, lambda. P equals h over lambda, where h is Planck's constant. Using this and some relativity for the electron's energy, he derived a formula for the change in wavelength, the Compton shift, that perfectly matched his experiments. It wasn't just another experiment confirming quantum ideas, it was. It was profound because it directly linked quantum mechanics, the photon concept, with special relativity, the electron's energy and momentum at high speeds. It showed this deep unity in physics, and it really cemented the photon as a real quantum particle, not just some mathematical trick. You notice this effect most with high-energy things like X-rays because their momentum is significant enough to give the electron a noticeable kick and lose a measurable amount of energy in the process.
Wow. Okay, so beyond these direct collisions, light interacting with individual atoms and molecules, that gives us another window, right? A way to see the quantized structure of matter itself. Light acts like a fingerprint here. Atoms and molecules, they don't just absorb or emit any old light. They're very picky. They only interact with photons that have exactly the right amount of energy to match the difference between their internal energy levels. Let's take atomic spectra first. Electrons in an atom, they live in these discrete energy levels, like rungs on a ladder, right? That was the Bohr model idea initially. So if you shine white light, which is all frequencies, through a cool gas, an atom can absorb a photon, but only if that photon's energy exactly matches the energy gap between two levels. That bumps the electron up to a higher excited state. This removes specific frequencies from the light, leaving dark lines in the spectrum. That's an absorption spectrum. Conversely, if you heat up a gas or run electricity through it, like in a neon sign, the electrons get excited. When they fall back down to lower levels, they emit photons with energy equal to that energy difference.
This creates bright lines at specific frequencies on the emission spectrum. And what's really fascinating here is that every element has its own unique set of energy levels, its own unique barcode, essentially. That red glow of a neon sign. That's the specific set of emission lines from excited neon atoms relaxing back down. And this is the whole basis of spectroscopy. It's how astronomers figure out what stars and galaxies are made of, even billions of light years away, just by looking at the light.
And molecules, well, they take it a step further. They have even more complex energy levels. On top of the electronic levels, like atoms have, molecules can also vibrate. Their bonds can stretch and bend. These vibrational transitions typically correspond to energies in the infrared part of the spectrum, and they can also rotate. The whole molecule can spin. These rotational transitions usually involve even lower energies, typically in the microwave region. So molecular spectra are much richer, often showing these broad bands of very closely spaced lines, which are actually combined vibrational and rotational changes happening together. And there are quantum rules, selection rules, that dictate which transitions are actually allowed. For instance, for a molecule to absorb infrared light via vibration, that vibration usually has to cause a change in the molecule's overall electric dipole moment. The point is, the incredibly discrete nature of all these spectra, atomic and molecular, turns light into this exceptionally precise probe. It reveals not just what chemicals are present, but also things like temperature, density, pressure, even the intricate 3D structure of molecules.
Okay, so that was a fascinating dive into the quantum world, where light is all about photons, discrete packets, specific interactions, tiny kicks. But what happens when we zoom out? When light interacts with bigger things, the stuff we see and touch every day, when does the wave picture take over?
Right. As the scale of the interaction gets bigger, moving from single atoms to, say, clouds of particles or bulk materials, that quantum granularity the individual photon kicks, it sort of averages out and becomes less apparent. The collective behavior of, well, countless photons acting together is much better described by the classical wave model. So here we think of light as an electromagnetic wave with properties like wavelength, frequency, and polarization, and its interactions scattering, reflection, refraction follow the rules of classical electromagnetism and optics.
Scattering is a perfect example. That's light getting redirected by particles in its path. And the crucial thing, the defining factor, seems to be the size of the particle compared to the wavelength of the light. Let's start with Rayleigh scattering. This is when the particles are much smaller than the light's wavelength. The classic example is the air molecules in our atmosphere, nitrogen, oxygen. They're tiny compared to visible light waves. The light wave, as it passes, makes the electrons in these molecules oscillate, wiggle back and forth. And these oscillating charges then re-radiate light, but in all directions. Scatter it. And here's the kicker, the really interesting part. How much light gets scattered is wildly dependent on wavelength. It goes as 1 over the wavelength to the 4th power. That means shorter wavelengths, blue and violet, get scattered way, way more strongly than longer wavelengths like red and yellow. So what does this mean for us? Well, it's why the sky is blue. That blue light from the sun gets scattered all over the place by the air, reaching our eyes from every direction. And sunsets. When the sun is low, the light travels through much more atmosphere. Most of the blue and green gets scattered away before it reaches you, leaving the less scattered reds and oranges to come straight through. It's beautiful physics painting the sky.
Exactly. But then if the particles are bigger, say comparable in size to the wavelength, or even larger, think water droplets in clouds or dust or pollen, then you get a different kind of scattering called Mie scattering. Now, Mie scattering is much less sensitive to wavelength, especially across the visible spectrum. It scatters all colors more or less equally. It also tends to scatter light more strongly in the forward direction, sort of along the original path of the light. So this explains why clouds look white or fog looks white. The water droplets are large enough to scatter all colors of sunlight pretty equally, giving that bright, diffuse look. And that hazy look you sometimes get around the sun on a dusty day, that bright glare, that's the strong forward scattering from larger aerosol particles, classic Mie scattering.
So it really boils down to that size comparison.
Yeah.
Tiny particles scatter blue light preferentially, making the sky blue. Bigger particles scatter all colors, making clouds white. Amazing.
And then, when the objects get much, much larger than the wavelengths, like mirrors, lenses, walls, us, we can often simplify even further and just treat light as traveling in straight lines or rays. This is the realm of geometric optics.
Yeah, like with reflection. Light has a smooth surface, like a mirror, bounces off. The angle it comes in at equals the angle it leaves at. Very predictable, like the billiard ball again. That specular reflection gives you a clear image. But if it hits a rough surface like paper, the light bounces off in all different directions. That's diffuse reflection. It's where you can see the paper from any angle, but you don't see your reflection in it.
And then there's refraction, the bending of light when it goes from one transparent material to another, air to water, air to glass. This happens because light actually changes speed when it enters a different material. We quantify this change with the material's index of refraction. This bending is governed by Snell's law, which relates the angles and the refractive indices. It's the fundamental principle behind lenses, how your glasses work, how a camera focuses light, why a straw looks bent in a drink. It lets us precisely control the path of light.
And finally, in this classical realm, light can just be absorbed. Its energy gets converted into another form, usually heat, within the material. This is fundamentally why things have color. A blue object looks blue because it absorbs most of the red, orange, yellow, green light and primarily reflects or scatters the blue light back to our eyes. And absorption is crucial for applications too, like solar panels. They're designed to be really good at absorbing sunlight across a wide range of wavelengths to convert that energy into electricity.
Okay, so we've seen light acting naturally as particles or waves. But what about when we get involved, when we try to actively manipulate light? How are modern technologies actually engineering these interactions?
That's a really exciting frontier. Modern tech, especially things like really high-intensity lasers and our ability to create structures on the nanoscale nanofabrication, lets us move beyond just observing light-matter interactions. We can actually engineer and control them in new ways. This introduces two really powerful new control knobs, if you like: the intensity of the light itself and the geometry of matter at incredibly small scales. Let's talk about intensity first. Normally, in conventional optics, a material just has its properties, a certain refractive index, a certain absorption. It doesn't care how bright the light is. But if you hit it with a really intense laser beam, you can push it into what's called a nonlinear regime. Suddenly, its optical properties do depend on the light intensity. What's fascinating here is a process like second harmonic generation, or SHG. You can actually take two photons of one frequency, say, from an invisible infrared laser, and the material forces them to combine into a single photon with twice the frequency. So boom, you get visible green light coming out. You need special materials for this, ones that lack a certain symmetry. But it's like you're forcing the material to do something it would never ever do under normal weak illumination. It opens up all sorts of ways to generate new colors of light and manipulate beams.
And the other control knob is nanoscale geometry. This leads us to the field of plasmonics. This is all about harnessing how light interacts with the collective oscillations of free electrons in metallic nanostructures. These collective wiggles are called plasmons. Specifically, if you shine light on a tiny metal nanoparticle, maybe just tens of nanometers across, the light can resonate with the electrons in the metal. This is called localized surface plasmon resonance, or LSPR. And when this resonance happens, you get these enormously enhanced electromagnetic fields, but they're tightly trapped right at the surface of the nanoparticle. This lets you concentrate light energy into volumes much, much smaller than the light's wavelength itself, something you just can't do with conventional lenses. And if we connect this to the bigger picture, the applications are amazing. Things like SIRS, surface enhanced Raman scattering, uses these enhanced fields to detect the unique vibrational fingerprint of even single molecules. That's huge for chemical sensing, medical diagnostics. Plasmonics is also key for developing things like metamaterials with unnatural optical properties, and potentially for building tiny nanoscale photonic circuits, routing light like we route electrons today.
Incredible stuff. Engineering light at the nanoscale. Okay, let's pull back one last time to the grandest stage of all, the cosmos. Light is our main messenger from across the universe, isn't it? How does it reveal stars, galaxies, even space-time itself?
Absolutely. On cosmic scales, light traveling for billions of years is pretty much all we have to go on. And stars, the basic building blocks, they emit light in a very particular way. To a good approximation, stars behave like black bodies. Now, that's an idealized concept, but it means their emitted spectrum, the brightness at each wavelength, depends only on their surface temperature. The shape of that spectrum doesn't really depend on what the star is made of or how big it is. Temperature is the absolute key. It's an incredibly pure thermal signal.
Right, and there are specific laws governing this black body radiation. There's Planck's law, which gives the exact shape of that spectrum curve, that characteristic hump, and it solved that ultraviolet catastrophe problem we mentioned earlier. Then there's Wien's displacement law. That one's really intuitive. It says the wavelength where the star emits most intensely, the peak wavelength, is inversely proportional to its temperature. So hotter stars peak at shorter wavelengths, they look bluer. Cooler stars peak at longer wavelengths, they look redder. Our sun, around 5,800 Kelvin, peaks right in the yellow-green part of the spectrum. Makes sense. And finally, the Stefan-Boltzmann law. This is the total power radiated, the total energy pouring out per second per unit area goes as the temperature to the fourth power, T to the 4. That means if you just double a star's temperature, it radiates 16 times more energy. A small change in temperature makes a huge difference in brightness.
Exactly. And astronomers use these laws all the time. They're like a cosmic toolkit. You measure a star's color, basically finding where its spectrum peaks. Wien's law immediately gives you its surface temperature. Then, if you can measure its apparent brightness and estimate its distance, you can use the Stefan-Boltzmann law to figure out its total luminosity, how much energy it's really putting out. And from that, you can even estimate its size, its radius. So just by carefully analyzing the light, we can deduce these fundamental properties of stars across the universe. Light is truly a direct thermal signature.
But the journey of that light isn't always straightforward, is it? Space isn't perfectly empty. There's stuff between the stars, the interstellar medium, dust, mainly, tiny solid grains. As starlight travels through this dust, it gets affected. This is called interstellar extinction. And crucially, just like with Rayleigh scattering in our atmosphere, but now with dust grains, these grains tend to be more efficient at scattering or absorbing shorter wavelengths, blue light, than longer wavelengths, red light. So what does this all mean for us observing from Earth? Two main effects, right? First, interstellar reddening. Because the blue light gets filtered out more, the starlight that reaches us is skewed towards the red. Distant stars look redder than they actually are. And it's important to stress this is a filtering effect. It's not the same as redshift due to the star moving away from us, the Doppler effect. It's just dust acting like a red filter. And second, there's dimming. The dust blocks some light overall, so objects appear fainter than they would if space were perfectly clear. Astronomers have to meticulously account for both these effects. They have to figure out how much reddening and dimming has occurred to get back to the star's true color and brightness, and thus its real properties.
Definitely. And perhaps the most mind-bending interaction of light on the cosmic scale isn't with dust, but with space-time itself. This is Einstein's general relativity. The theory tells us that mass and energy warp the fabric of space-time around them. And light, even though it has no mass, follows the contours of this warped space-time. It travels along paths called geodesics. So if space-time is curved by a massive object, light passing nearby will follow that curve. To us, it looks like the light path has been bent. This is gravitational lensing. And it comes in different flavors, revealing different things. You have strong lensing, where a really massive foreground object, like a whole galaxy or a cluster of galaxies, bends the light from something behind it so much that you see multiple distorted images, or these amazing bright arcs, or even a complete circle called an Einstein ring. Strong lensing acts like a natural cosmic telescope, magnifying extremely distant galaxies we could never see otherwise. Then there's weak lensing. Much more common, much more subtle. It just causes tiny, almost imperceptible distortions in the shapes of background galaxies across large areas of the sky. But by measuring these tiny distortions statistically over millions of galaxies, astronomers can map out the distribution of all mass between us and them, including dark matter, which doesn't emit light but still warps space-time with its gravity. It's our main tool for mapping dark matter. And finally, there's microlensing. This happens when a single star, or even a planet, passes almost directly in front of a more distant star. Its gravity briefly focuses the background star's light, causing a temporary characteristic brightening. This has become a really powerful technique for finding exoplanets, even small ones, orbiting other stars. So in this cosmic realm, light isn't just carrying information about its source, its path becomes a tracer. It reveals the very geometry of the universe and the distribution of all the matter within it, visible and invisible.
What an incredible journey that was. Seriously, we've gone from the quantum realm, with photons kicking electrons out of metal, to classical waves scattering in the atmosphere to give us blue skies and red sunsets. Then into the lab, engineering light with lasers and nanostructures. And finally, all the way out to the cosmos, where light's path traces the shape of space-time itself. What's fascinating here, the real unifying thread, seems to be that the scale and the nature of the matter involved dictates how light behaves, and which face it shows as wave or particle. Light isn't really one or the other, is it? It's this complex quantum entity that just answers the question you ask with your experiment. Almost like it obliges us by showing the behavior we're set up to detect.
Exactly. It's this deep complementarity, and it leaves you with a rather profound thought, doesn't it? Considering how these very specific interactions, these carefully designed experiments, are required to reveal one aspect or another of light's nature, what does that tell us about the role of measurement itself? How much does the way we ask the question shape the reality we perceive? Are there potentially other, maybe even stranger, aspects of fundamental particles just lurking beneath the surface, hidden only because we haven't yet figured out the right experiment, the right question to ask to make them reveal themselves?